All right, students, this is going to be a review for the momentum unit. I'm just going to go through all the information as quickly as possible. There's going to be a lot of review from the previous units that deal with the momentum unit. All right, so let's begin. So first things first, the equation for momentum is P is equal to m times v, where if you have an object that is moving, it is said to have momentum. And the units for momentum, it's either kilograms times meters per second or Newton second. So either one works. And the variables for momentum is P for momentum. Okay, and we can't talk about momentum without talking about impulse. Now, impulse is not a force. Okay, impulse is the change in momentum, and we represent impulse with the capital J. So the change in momentum is mvf minus mvo, because we always do final minus initial for momentum, and that can be found by force times time. Now, in one of the quizzes, there was a question about, is impulse a force? And some of you might have said, yes, it is a force. That is not true. Impulse is not a force. It's not a type of force, right? So we know the force of friction, the normal force, the force of gravity. Those are actual types of forces that might cause a impulse. Simply put, impulse is this right here. It is a change in momentum. So if an object's momentum changes, we say that the object experienced a impulse. Right? So there was some kind of force that caused it to have a change in momentum. All right. So from there, I want to go into the big ideas of the graphs. Okay. So remember, for a slope, if you have a slope, it's always going to be y divided by x. And so in the equation, if you have anything that is being divided, those two variables that are divided is equal to whatever the slope might represent. And then we have area under the curve, and area under the curve is y times x. Okay, and that's in multiplication. So within the equation, if you have the two variables that are being multiplied, that shows you the area under the curve. And if you have the two variables that are being divided, that is the slope. So if we take a look at the momentum equation, we have P is equal to m times v. So from here, there's a couple of things that we can look at. Now, you won't really see a mass times velocity graph. Like that's not a thing you'll see. But within here, we have this velocity equation. And this is one of those reminders. Remember, velocity is displacement divided by time, or change in position over time. And so if we take a look at this equation right here, we can apply what we just discussed up here with the slope and the area under the curve. Because the position and the time, they're being divided, if you are dividing the two, so we have position versus time, whatever the slope is the velocity. Okay. Now, if I were to rearrange this equation and we get x is equal to v times t, right? I just moved the time over on the other side of the equation. Because these two variables are being multiplied together, that is the area on the curve. And so we have velocity times time. Therefore, like if we get something like this, I don't know. Oh boy. Whatever this area under the curve is, that will be your displacement. Okay. All right. So that's how you know if you're doing area under the curve or if you're using the slope. And so for a problem that you might see using this momentum equation, because of this velocity here, they might ask you a question that deals with velocity, right? So they could give you a position versus time graph, or they could give you a velocity time graph. And from there, they could ask you what the momentum is, or they could even ask you what the change in momentum is, because if we take a look over here on the under the impulse equation, right, we see that there's a change of velocity here, and so from there we would just take a look at the points of the graph. But let's go back to here. There's velocity. So if you're given a position versus time graph, and that means you should be able to find the slope. Right? So with that slope, if you multiply that value for the slope by the given mass of the problem, you should be able to find the object's momentum. And from there, the question can go further and ask you a little bit more in-depth questions about the change in momentum. All right. So let's take a look at the impulse equation. So impulse, there's a lot of things that are being multiplied, but what I want to focus on here is not the first two variables here, but the latter half. So mvf minus mvo is equal to f times t. So I want to break this equation down even more, because that is just m times the change in velocity is equal to force times time. Okay, so here we have two things that are being multiplied. So if you ever see a force times time graph, right? So force, time, this, because it's being multiplied, remember, if you're multiplying, you're looking for area under the curve. So if you're given something, I don't know, something like this, right? Here, I'm going to color it in, but this area in the curve, that can be impulse 1, right? So whatever the change in momentum is, will be that area under the curve. And so, for example, if your initial momentum, let's say your initial momentum was, I don't know, 5 Newton seconds, right? That's your initial momentum. And they give you this graph, and they say after the impulse of section 1, what is the new momentum, right? So that gives you the change in momentum. And let's say this area in the curve, let's say the area on the curve is, I don't know, 10, right? 10 Newton seconds. And so after section little 1, because the change in momentum is 10, it will be 5 plus 10. And so the final momentum after section 1 will be 15 Newton seconds. So that's how much it changes by. This doesn't actually give you the momentum, but it gives you the change in momentum. Now, if you started off with no momentum, whatever this area under the curve is, that would be actually your final momentum. But you know, if they give you your initial momentum, you can't use that strategy. All right, so here we have underneath the x-axis, here we have a negative impulse. So this is a negative area in the curve. We'll call it the section 2. And let's say this is like, I don't know, negative 15 Newton seconds, okay? So we have positive 15 and we have we have positive 10 and negative 15. And so if the question asks you, after force 1 and force 2, right, these two sections, what is the new momentum? Okay, all I gotta do is find the total area in the curve. So I have 10 plus negative 15, which gives me negative 5. So that's my change in momentum. Okay, so I'll write that down. So the change in momentum after 1 and 2 is 10 plus negative 15, which just ends up with negative 5. Okay, so that's my change in momentum. And if we use the change in momentum equation, which is final minus the initial, right? So if my final momentum is negative 5 and my initial momentum is 5, okay, I did that incorrectly. We're looking for the final momentum. So final momentum is, we don't know, minus the initial momentum, which is 5, and we know that the change in momentum, right, the change in momentum is negative 5. There we go. So mathematically, if we add 5 to both sides, we will get 0. So after impulse 1 and impulse 2, our final momentum will be 0. Okay, so that's the strategy that you will go about it. And we did that because we know that in the equation, force times time is being multiplied. Okay, multiplied. All right, so that is impulse and that is momentum. All right, so the other thing that we covered in this unit were the types of collisions and how it deals with energy. So there are, let's see, 3 types of collisions. 3 collisions. So collision type number 1, we'll call it perfectly elastic. Oh my gosh, that's not a perfectly elastic collision. Now, in a perfectly elastic collision, we have 2 objects, and those 2 objects, they collide, and after they collide, they bounce back apart. Right, so that's your initial, and the final, they bounce, and I'm just going to say they rebound like this, but it doesn't have to. But the main idea here is that for perfectly elastic collision, kinetic energy is conserved. Okay, that is always true for a perfectly elastic collision. No energy is lost. And the other thing that you need to know is that momentum is conserved. Okay, momentum is conserved. Now, how do we solve these types of problems? Well, if you remember, we use the conservation of momentum equation. Okay, so in order to do the conservation momentum equation, trust me when I say it really helps if you do sketch it out, okay, based on what the problem is saying. Sketching it out, even like, for example, if they give you a work problem and they don't give you a image to work off of, you should be able to create your own images, and you should be able to label that image so that you can create the equations. So the first thing for conservation of momentum, right? Momentum 1 plus momentum 2 is equal to momentum 1 final plus momentum 2 final. right? So all I did is I just, I said there are two objects, and those two objects both have momentum. And because at the end of it all, there's two objects, and both of those two objects will have momentum, I just created that formula based off of what I just said verbally, right? Two objects, two momentums is equal to two objects with two momentums. So that is how the conservation of momentum works. The momentum you have initially, okay, and the initial is always on the left, is what you have after the collision, which is the final. Right? And from there you can replace P with M times V and go on from there. All right, so the second type of collision is a inelastic collision. Now for inelastic collision, we usually say the two objects, they stick together, right? We have a system where the two objects stick together. So for example, if we have object 1 is moving to the right and we have object 2 that's moving to the left, after they collide, the two objects are stuck together and we'll say it just moves to the right, kind of like that. Okay, so same strategy. I count the number of objects I have. I have P1 plus P2. And after the collision, I say we have P1 plus P2, right? So in my subscript, I show that they collide and they combine. Now, this is extremely helpful when you do the formula version, right? When you extend it out. Because here, when we extend it out, we say that the parentheses show that the two objects have combined, right? M1 and M2, they have combined together. Okay, and so that's how you would come up with the equation for the inelastic. All right, now important things. Inelastic, anytime energy is lost. Okay, so that means that energy is not conserved. Anytime energy is lost, you have an inelastic situation. But the important thing is that momentum is always conserved. Okay, momentum is always conserved. All right, the last situation is the explosion. Okay, the explosion type of problems, and that's when we have two objects that are stuck together, M1 and M2, and for whatever reason they fly apart. Okay, so let's say it was originally moving to the left, and whatever explosion happened, right? Two objects go flying apart. And so what the equation would look like would be the reverse of the inelastic. So we will say P1 plus P2 is equal to P1 plus P2, and we will say M1 plus M2 V is equal to M1 V1 plus M2 V2. Okay, it's the reverse. Now, because it's just like an inelastic problem, the same properties follow. Energy is usually lost. Okay, and momentum is conserved. Now, you'll notice that momentum is conserved for every single one of them, and that has to hold true because otherwise we can't use the momentum, the conservation of momentum equation. Okay, if this statement was not true, we can't use this formula, and because it is true, we can use that formula. Right. Now, with that, right, those were the three types of collisions. There was something very important that we learned. We learned a different technique, and we learned a technique where we could combine all three of these situations and look at it from a different viewpoint. And we took a look at the viewpoint called the center of mass. Okay, or the system's center of mass. And so what that says is that it doesn't matter for the center of mass, right? The center of mass. So for the center of mass, the big idea is that unless there is an outside force, the momentum of a system cannot change. Okay, now this goes with Newton's laws, and this is something that you should definitely have memorized by now. I do know that if I ask my students, sometimes they don't remember this, and it brings me great heartbreak because this actually makes life so much easier. Okay, that is definitely a highlighting one. If there's an outside force acting on a system, the momentum for a system cannot change, and that holds true for usually for energy things as well. So what this means is, let's say we have two objects, right? We have object 1 that's like really, really big, and we have like object 2 that's kind of a little small. So the center of mass, if you remember, is the average distribution of the mass, and so we can say, so normally the center of mass for the big object will be right there, and normally the center of mass for a small object will be right there. Okay, those two little dots. But because we have two objects that are stuck together, the actual center of mass, I'll do this a little bit bigger, is like an average point somewhere in between. Okay, now I had a other videos with center of mass, and I do encourage you to look back into it because it is a big main idea. So let's say these two objects are moving forward like this. We can take a look at the situation where each center of mass, where each object has its own momentum, but it is easier to look at not the two objects individually, but just the center of mass of that one of the system. And the center of mass of the system can be represented as a dot. So we can say that this center of mass, this dot, has a velocity that is going to the right. Okay, and that red dot represents both of these objects. And it doesn't matter if these two objects break apart, right? So if it's an explosion type of problem, right, that goes flying that way and this goes flying this way, it doesn't matter how that works out. The important thing is that the momentum of the center of mass, that never changes. This will still move forward. Okay, because if the original center of mass's momentum is moving forward, okay, forward momentum, the final momentum must hold true. So that means that the center of mass has the same velocity moving forward. Now, the reason why this is helpful, not only for situations like this, but because if you have a situation where like things aren't really changing, right, but like the problem is asking you, where will the new location be? Okay, what they're really asking you is according to the average center of mass. Okay, so if the average center of mass is here, if we know that object 1 is here and object 2 is all the way out there, the average center of mass should be there. And so the problem could ask you, let's say we don't know, I'm gonna box this one. We don't know where this one object is. The question can ask you, where do you think logically this object is located if we know that object 1, or the object that's flying to the left, is located here, and we know that the center of mass is right there, right? And so from there, you should be able to logically conclude that this object has to be somewhere to the right. And depending on the ratios of the size, it has to be, how far away from either object. Now, the other thing that's helpful for this is knowing how much momentum each object will obtain after an explosion or an inelastic kind of collision, because we know that this momentum for the center mass, that can't change. And so this is showing you the average, right? So this is showing you the average momentum for both objects. And so if this object is moving to the left, and we know that the center of mass has a momentum going to the right, that must mean that this object, okay, we'll just call this object 2, object 2 must have so much momentum to not only override this leftward momentum, but override this momentum and to give the center of mass a momentum to the right, okay? Because as is, if we don't look at object 2, this momentum to the right would change, and that will be a momentum to the left. But because we know there were no outside forces, the momentum has to remain going to the right. Which means that object 2 has such a great momentum. It's moving super fast, even though it's tiny, it's moving super fast, so that the overall momentum will be going to the right. Okay? All right. I talked a lot about center of mass there. In the actual center of mass video, I go over very specific examples, and I do encourage you to all go and watch that video. Again, you will, trust me when I say, come across example problems where you have both explosion problems, elastic problems, inelastic problems on your exam. Now, the other thing I do want to highlight is the equation itself. At this point, I trust that all of you are able to find an equation, plug in the numbers, and solve it. That's not the hard part. The hard part is able to get these equations, right, and put it into the context of the problem. So here's my strategy. Okay, we are deep into the curriculum enough so that you should be able to use these different kinds of strategy. You should be able to, 1, look at the problem. Okay, 1, look at problem. 2, identify variables. Identify the variables. So what this means is if you're given a graph, okay, look at the x and the y axes. Look at those variables, right? If it's a word problem, if you are able to write down, like if it's talking about speed, if it's talking about velocity, if it's talking about position, if it's talking about those forces, right? Even if they don't give you a number, write down those variables, identify the variables. And from there, find your equation. Okay, find your equation. Because the problem most likely isn't going to be, hey, can you plug in these numbers and find an answer? But rather, it's going to ask you about different kinds of relationships, right? Inverse relationship, directly proportional, inverse square, those kinds of things. And right now, at this moment, you should be able to look at an equation and know what those relationships are. For example, if we take a look at P equals MB, okay, we don't see any squares here, so we don't have to worry about any kind of square relationship. But what we can look at is how each variable affects each other. So my strategy, when we first started out, I said give each one of those variables the number 1. 1 is equal to 1 times 1. So if we were to increase the mass by a factor of 2, right, 1 is equal to 2, what would V be? Right? So 2 times what gives us 1, and that'll be 1/2. And so when the mass increased, we can say that the velocity decreased. Okay, so this is what we call an inverse relationship. And the best way to look at it is see where they are located within the equation. If you're next to each other, inverse. If they are opposite sides of the equation, that's usually a directly proportional. All right, and luckily for us, for this momentum unit, all the variables are directly proportional to each other. All right, next thing, once you find your equation, here's the most important part. You gotta actually freaking solve the problem, right? And that actually links up with number 2. What is the question actually asking you for? Okay, the question itself is a variable. If it's asking you to find the time, that is part of your variables. Look for the time. Okay, write that down. Identify the variables and go from there. All right. So this is a strategy that you should be using for your multiple choices and your free responses once we get to that point. And trust me when I say you will see a lot of graphical stuff. So brush up on that. Give yourself a quick little pep talk. Sketch different kinds of graphs that you think you'll see based on the equations that I highlighted. You need to know the concepts, the big laws. Elastic, okay, everything is conserved. Everything but elastic, everything is conserved, right? For every other kinds of collision, energy is lost, but momentum is always conserved, okay? And when you're solving these, have a notebook ready, right? Sketch things down. You don't have to copy down the problem, but sketch it out, jot your ideas down, and identify your variables. All right, so that's that for the momentum review video. I don't think there is much else I can really talk about. If you do want a more in-depth analysis of the unit, go back, look at the other videos. Trust me when I say they do help. All right, bye-bye.